this is Calculus 12, Chapter 2.3, Part 1. This time we're going to be looking at continuity. And the big idea is if we can draw a function without lifting our pen, then the function is continuous. However, in math, we need to show this with limits and theorems. So, big idea is this is continuous. And if we do this, this is discontinuous. Okay, we'll start with some definitions. A function f is continuous at an interior point of A of its domain if limit x approaches A of f of x equals f of A. Okay, so if we have f of x, if the limit of x approaching A equals f of A, then it's continuous. So this point should be on the curve. If the point is off the curve, then discontinuous. Okay, so if the point is off the curve, then it's discontinuous. If it's on the curve, then it's continuous. So if f is not continuous at A, then we say f is discontinuous. Rather than saying not continuous. At A and A is a point of discontinuity. So sometimes you're going to make a mistake and you're going to say not continuous, that's fine. But try to learn to say the right things most of the time. Definition: a function f is continuous at a left endpoint A of its domain if limit x approaches A from the right of f of x equals f of A. Okay, so a left endpoint looks like this. So we have to approach it from the right. And then similarly, a function f is continuous at a right endpoint of A of its domain if limit x approaches A from the left of f of x equals f of A. Okay, so endpoint f, so we're approaching from the left. So we have different types of discontinuity. This one is called infinite discontinuity. Here we have point discontinuity. And we want to note that it is removable. Here we have a jump discontinuity. And it's not removable. And this is missing something. There's a dot here. This is a point discontinuity. And this point is removable. Okay, so it doesn't matter whether the point's defined or not defined. They're both removable. And here, the jump discontinuity. This is all fine for a graphical solution. If you wanted to do a algebraic solution, you have to show that limit x approaches c from the left of f of x does not equal limit x approaches c from the right of f of x. And if we look here, the left is actually equal to -1, and the right is equal to 3. So -1 does not equal 3. Okay, and point discontinuity is removable. And we can remove this discontinuity using a piecewise function. So let's take a look at an example. Okay, here we have a rational function. And with rational functions, the discontinuity is going to be at our NPV, so x equals 2. So we take the limit, x approaches 2, f of x equals limit x approaches 2, we substitute the function, x squared minus x minus 2 over x minus 2. We factor the numerator because we want to cancel out terms, x minus 2, x plus 1 over x minus 2. The x minus 2's cancel out. So we have limit x approaches 2 of x plus 1. And we should break this up into terms. Limit x approaches 2 of x plus limit x approaches 2 of 1. That equals 2 plus 1, and that's 3. So we need to remove the discontinuity. We want f of 2 equal to 3. And we're going to do this with a piecewise function. We should use a different letter from f. Okay, so we can use f here, or we can write out this. So it's going to be f of x when it does not equal our NPV. So x does not equal 2. And when it does equal our NPV, x equals 2, we want it to be equal to 3. Okay, so for our piecewise function, make sure you put the function, a comma, and the domain for that partition. And just to reiterate, this is a piecewise function. Okay, we have another type of discontinuity. I graph this rather than drawing it by hand. And this is y equals sine 1 over x. So as it goes closer and closer to 0, it's going to be oscillating faster and faster. And if we try to take the limit as x approaches 0 of this function, 1 over x, it does not exist. And it's because it's oscillating faster and faster as it gets closer to 0. So it's not going to actually reach a particular value. It's just going to keep oscillating up and down. Let's look at another problem. And we're going to answer this graphically. Then we're going to do it algebraically as well. And I'm just going to keep on saying this until you memorize it. Piecewise function. So we have 5 partitions. Okay, let's answer these questions. We're also given the graph, so that's really beneficial, so you don't have to try to figure out what all this means. This is x squared minus 1. This is 2x. This is 1. This is negative 2x plus 4. And this is 0. So we need to answer these questions. Does f of 1 exist? F of 1, yes, it's right there. So f of 1 equals 1. B, does limit x approaches 1 of f of x exist? And limit x approaches 1 of f of x. That equals 2, because it's getting closer to 2, getting closer to 2. So yes, it does exist. Oops, there's a 1 there. Does the limit x approaches 1 of f of x equal f of 1? And the answer is no, because 2 does not equal 1. So we figured out the two answers there, they're not equal. Is f continuous at x equals 1? No, because of our answer C. Okay, algebraically. Well, we just did this one. There's really no algebra involved. You just look at the piecewise function. It's not the same as this. Look at piecewise function. Part B. This one involves a little bit more work. Limit x approaches 1 from the left of 2x. That equals 2. Limit x approaches 1 from the right of negative 2x plus 4. And we should break this up. Limit x approaches 1 from the right of negative 2x plus limit x approaches 1 from the right of 4. Substitute this in, that equals negative 2 plus 4, that equals 2. So limit x approaches 1 from the left, and we'll just make it easier by saying f of x equals limit x approaches 1 from the right of f of x. So limit x approaches 1 of f of x equals 2. And it exists, so yes. And again, yes. Okay, part C. So from A, answer A does not equal answer from B, i.e. that is 1 does not equal 2, so no. And from answer C, no. Okay, since the limit does not equal the value, it's not continuous. And just a reminder, the 3 dots means therefore. And that completes this lesson.